99.999%.
Well, yeah, we're not saying any sign.
Let me ask you a question. Have you ever eaten food before?
Very likely, yes.
You
can't say I'm not consistent.
Well, okay.
I can say that.
Go with that.
Consistent, but...
Well, I could say it, whether or not it'd be true or not.
It blows my way.
It's very likely
it
that
might
I've
be
eaten food. I mean,
how did you get this far?
Yes. Let's not Rumpus Indio. She was... I don't know, are you?
I'm saying, how did you get this far? In order to, survive,
I'd consider
you need to eat food. You're more than 1 day old. So, listen, we can know things for certain. It is 100% for sure that you ate food before. There's no doubt.
What if
there
we
is
live
no
in a
doubt.
simulation and, maybe we aren't eating food. We just think we are. I'm not actually considering that, by the way, but...
A simulation
I'm
of
trying
what?
of our world. No, it's...
Electrons.
What I'm saying is that there's always...
It's a simulation of the simulation of ourselves. It's like a snake eating its own
very
tail.
Meta.
Simulations.
Very meta. Very meta.
Well, anyway,
no, basically,
what I'm saying probability is a logical fallacy, but we can go with that just for the point of conversation.
Sure. But for
you have
all
confidence,
practical purposes,
I want you to
can say that I know that I ate food.
Okay, so I want you to serious ask you. What was your question again? Serious, ask me again. I don't want to word it wrong.
My best proof for the globe was.
Yeah, simple question. Yeah. Proof, it's nothing. Okay, I'm with you. Measurement. I love metrology. Everything is within tolerance, plus or minus something. I know. I understand. There's nothing like absolute. Yes.
Sure.
However,
great.
So,
awesome.
Give me your
yes, I have one.
Give me your tolerance, and I'll work within that.
I will say I don't have the numbers in front of me right now, but
whatever it is,
the data is publicly available if you want to go into the numbers more. And I would love to go into the numbers.
I love numbers. We'll get into it.
Gotta love numbers. But to introduce you to the basic concept, there is an experiment called the Minos neutrino experiment. Have you ever heard of it?
No, I am unaware of it.
It's a particle physics experiment.
Yeah.
You see it now. Yeah.
Mike likes neutrinos, I guess.
Neutrinos are great. So.
Bullshit's great too.
Neutrinos are a type of radiation. Neutrinos are a type of radiation that can be emitted by radioactive particles. And neutrinos are very odd in that they can pass through a very large amount of solid material before they interact with something. So you could potentially stand directly in front of a neutrino beam and not even notice. Yes,
how about you don't talk to us like we're ignorant to it, and how about you don't just assume that you're teaching us something new? How about that?
Oh, he's teaching some people.
You do know what neutrinos are?
He's cool, man. He's cool.
Yeah, no, I just don't want to blow past.
I just said all that to blow hot air out my mouth.
Cyrus, I do not know.
You're not the first person that came in here with the little neutrino thing. I'm well aware of the minus. Who used to come in here? Gold Steel?
Mm-hmm.
Yeah, so we've heard this all before.
I think I know of him from the Quantum Racer server. Yes. Anyways, so the Minos neutrino experiment is one of actually several experiments of this variety, where they have a generator that creates a beam of neutrinos in Illinois at Fermilab, and it shoots these neutrinos through the Earth at a target in Minnesota. So it shoots through the solid rock of the Earth into that detector in Minnesota. It's very, very cool. The main purpose of this experiment is to find the whole difference between matter and antimatter that we were mentioning earlier. But a secondary benefit of this experiment is that in order to actually aim at that target, it has to be angled downward at, I forget, 10 degrees, 5 degrees, something like that. The whole beam pipe is at a slope.
And, did they ever not? So when they built this, did they ever not angle it down?
Well, no, they never didn't.
No, so they never tried to angle it in any other way, right? Said, "Oh, it's there, so this is what we're going to do."
The neutrinos come out in a straight line. It's like firing a gun.
Oh, they're measuring the angle of arrival, right? What you're saying?
Yes, they are. They're measuring the angle of arrival as well. Yes.
Okay. How is that performed?
Well, so they use a neutrino detector, which is, how do I describe it? It's a series of
array, like
it's sort of an array of striped pipes full of, I believe, liquid argon. And what happens is that when a neutrino interacts with this liquid, it lets out a small flash of light. And that flash of light is then collected by scintillating fibers, which then funnel that light into a photomultiplier. Basically, it senses small amounts of light and gets recorded in a computer. And what they can see is that from this array of pipes, which are pretty deep as well, like there's many rows and rows of these behind each other. And by seeing which pipes get lit up, they can recreate the track of the particle that entered it. And so from that you can calculate the angle of arrival.
And this applies to the argument at hand, how?
Well, if the Earth was flat, and this neutrino detector is angled at this downward slope,
inside the Earth.
It was a hot air balloon they sent up.
Right.
And they found that neutrinos were just like coming out of the ground.
That's a different experiment. That's
I know, but they still found out that neutrinos were just coming out of the ground.
So how do you isolate from the, okay, I'm going to ask you because I know nothing about this. So how did they isolate the neutrinos that are coming out of the ground from what's being shot?
But they were detecting them
that's a good question.
Here, hold on, dude.
Isolating background radiation is a very
important
step in particle physics.
Hold on a second.
What were you saying, Indio?
What I said was, I think it's called the Ice Cube 2 was a test they did, experiment in quotations. They're measuring neutrinos, cosmic rays. But the results of the measurement was that neutrinos were just coming from the Earth when they were supposed to be coming from space.
The sun, right?
Well,
no, they were just coming from the Earth. They didn't have. There's no explanation for it.
Right, that's where they found them coming from.
There is an explanation, and that's that they are very high energy neutrinos, and that they entered in one side of the Earth and out the other, essentially.
That's one theory.
Neutrinos something they made up because Einstein was wrong about matter increasing mass as it approaches.
So I would like you to separate from this what is part of elementary particle theory and what is actually testable and refutable and demonstratable.
Sure. Well, this is my area of expertise. Okay, so we got we have a lot of different questions that are all very good. Which one should I tackle first?
What is a neutrino?
Separation of reality.
That's a great question.
Box out. We already talked about that.
It's an elementary particle.
Do we not want to talk about what a neutrino is, or?
Well, didn't you already define it? I mean, okay, go for it. Well,
I briefly explained what a neutrino was, but if you want me to go into more depth about like how they were discovered and how we know they're real, I can totally do that.
I was still waiting for proof of the Earth, man. You started off with proof of the Earth, and then
I guess this requires a bit of background.
Okay, so the proof of the Earth.
That they're shooting neutrinos through the Earth and picking them up somewhere else.
Yeah, right. And it has to be shot at an angle. If the Earth was flat, this beam would be undershooting the target, and they would never actually reach the target.
Oh.
Certainly wouldn't reach the target at the angle that is observed.
You're talking about the ball?
It does reach the target.
Well, you never really established how they're actually measuring the angle. I still don't get it. How did they measure the angle?
Is it to plumb? To level? Like the angle.
Yeah, like how do they determine like their relative positions, right? Their orientation relative to each other, right? From the detector to the neutrino. Let's call it the source and the receiver, right?
The detector is leveled to a plumb, so it's just on a
So how do they account for deflection of the vertical?
In what sense?
Because in the globe model, the plumb isn't a straight line that goes down.
Ooh, he didn't know that.
I'm not sure
something called deflection. A plumb is not a straight line that goes down. The gravity vector is not straight down, perpendicular to the surface. The globe model. There's something called deflection of the vertical. So some places it's straight down, but other places it's not. Depends on where you are. In Australia, it's particularly bad. So it's really like the alignment. If you really want to know what they think is that the alignment of astrogeodetic measurements don't actually align with the ground exactly.
To how many degrees does it vary normally?
0.7 is the largest I've seen.
Okay, well this is much larger than 1 degree. This is like on the order of 5 to 10 degrees, I believe. Actually, let me pull up these numbers because I hate guesstimating this.
What's 5 to 10? The canon?
Let me post things in the chat.
I mean, when they dig mine shafts,
there's a lot of assumptions here. This is really a problem. That there's so many assumptions here. In like, they're testing the angle and this that. But they never tried it any other way. It's not like they just like shot the beam horizontal and they were like, "Oh, we didn't detect it. Let's aim it down. Let's just keep aiming it until we."
Oh no, this is. I think you misunderstand the kind of proof that I'm trying to explain here. Firstly, this is...
Well, you're saying that this can only work if the Earth's a globe. I understand what your proof is. I completely understand.
Or
evidence, right?
Or rather, it definitely could not work if the Earth was flat. That is what I'm saying.
Yes.
Why so? Yeah.
So
last time we got here, I said why so.
If the Earth was flat, then the beam would be undershooting the target. It's aimed at a pretty significant downward angle.
This is where we get distance. And this is where we get into the and
if the Earth was flat, it would be down.
Is that you're doing statistical correlations between you're turning this beam on, you're picking it up, but we also know that you're going to pick up random neutrinos from anywhere. Right?
Yes.
You can't differentiate any model. The neutrino came from your beam or it came from somewhere else.
There's a fairly easy way to differentiate neutrinos that come from the beam and neutrinos that come from elsewhere.
How is that?
A model.
And that is
velocity. No, I'm just
partly. However, the main thing you do is you leave the detector running without the beam shooting anything at it, and you collect all the different types of radiation that appear in it from just the environment. And then you turn on your beam and you take the difference between the two. And that difference is going to be the signal from your beam, because that's the only thing that changed.
Okay.
Does that make sense?
Because, yes, it does make sense. But all you are is comparing probabilities.
Sure. I don't see
what's sure. You're just look, you're just comparing probabilities. You have a model that says you should have this many detections per time, right? Per unit time, if we turn the beam on versus the beam off. And you're saying these don't match. And you're drawing conclusions that, oh, the Earth must be curved because why else would it happen? It's not really proof of anything. It's really just saying I have confidence in my model. That's literally all you're saying.
Well, actually, you don't have to actually start out with that model. You can see if that difference is significant, regardless of what you're expecting to begin with.
So what's?
I always think of it like this, right? This is the way I always think of it. If the Earth measures flat, how does this experiment falsify that? Right. So we can talk about all these theories, right?
If the Earth was flat.
If Earth measures flat, so if we do measurements of the Earth that show that it's flat, how would this experiment falsify that? So if I have a table, right, and the table's 48 by 48 inches, I take out my tape measure, I measure it, and then there's some observation I make of a phenomenon, and it says, "Oh shit, this can't work with a 48 by 48 inch cable. My tape measure must be broken." You see what I'm saying? So I measure what's actually there. Like, how does this experiment falsify that? Yeah, that's how I look at it. How can you falsify a direct measurement of the surface of the Earth?
Something must clearly be wrong with your ruler then. If you have an experiment that does not agree, then clearly
maybe the experiment's wrong
when you do the first measurement.
But maybe the experiment's wrong. Ever think of that? Maybe the assumptions of the experiment are wrong, and it's not the measurement that's wrong.
No, thinking about how this experiment could be wrong is
there's inference versus deduction, right? Induction versus deduction. So you have a theory, right? A theory of how this thing works, right?
How would
you make all these indirect measurements, where we're talking about a direct measurement of what it is, right? Like, I can measure a person that's 6 feet tall, and my rulers can say they're 6 feet tall, and I have this thing that says, like, this light is supposed to be, 5'10", but the light, he walks past the light and it didn't shine on his head. He must not be 6 feet tall.
So, I'm a little bit confused about what you're defining as a direct versus indirect measurement.
Direct measurements, where you directly measure what it is you're trying to figure out what it is.
You defined direct by using the word direct, so that doesn't really help me out here. So,
well, it has a colloquial definition, doesn't it? You're supposed to have a PhD, aren't you?
Yeah, no, and that's why it's incredibly important to
words are defined.
Where's the measuring?
Words are defined by usage.
Direct measure refers to measuring exactly the thing that you're looking to measure, while indirect measurement means that you're measuring something by measuring something else.
I don't see how the angle wouldn't work.
And measuring through neutrinos would be an indirect measurement of something. You're not directly measuring the Earth, right?
Well, let's take that ruler example for a moment.
I don't see how that beam angle wouldn't work.
Yes or no? You're directly measuring the Earth. Yes or no? It's real stuff. You know that you're not. So, be honest.
Yes, but
you know that you're not. It's an inference from an experiment.
Are we not allowed to use inference? I don't.
Yeah, but when it comes to actually proving things in actual logic, there's certain things. Inference is secondary to deduction.
Inference is, well, yeah, but you have to show what's actually wrong with the inference, though, if you want to dismiss it. You can't just throw it out because
direct measurement to the contrary. Direct measurement to the contrary.
Direct measurements have their place, but they can be very limited. For instance, if you're trying to do direct measurements of the curvature of the Earth by, shining lasers over bodies of water, you're only going to be able to do that over very short distances. A laser can only shine so far.
How far is that?
Not
depends on the millirods. It depends on the millirods, actually.
Not 700. How long? What is that in miles?
You're
asking me to use miles?
Divide by 1.6. Yeah. Here, I'll fire it up.
American, dude.
Calculator. What was it?
730 kilometers.
730 divided by 1.6. 456 a quarter. So, do you need that?
Actually, somebody in the chat just posted the success here.
Do you need 450 mile differential for test for curvature?
How about 897 kilometers?
For a very big sphere, you need a very big
wait, hold on.
Measured.
He just outdid. Hold on.
So, hold on. I'm reading this real quick. So in 1914, there was a ship in the. I'll just read it to you. It was off the coast of South Korea. It's off the coast of Korea, and they watched the sun set behind mountains, and the only mountains that possibly they could be seeing were 897 kilometers away.
Wait, I thought
490 nautical miles. This was reported in some
Russian. You said we aren't allowed to use indirect measurements, though.
Oh my god!
No, listen.
Can you not interrupt him when he talks?
I did not say that was a direct measurement. What I'm saying is,
okay,
this is the same type. It's the same type of inference as you're saying, and it's further away.
Well, that's an interesting experiment. If you link it to me, I'll go look over it.
It wasn't an experiment. It was an observation from a ship.
Okay.
In the 1900s, the three officers of the ship watched the sunset. So, according to the heliocentric model, we know where the sun's setting, right? So they know the angle where the only place the sun could be setting, right? So they drew a line, or it was rising actually. So they drew a line to where it intersects land, and that land is in Japan. There's no other land in that ocean.
So a bunch of sailors. How many years ago was this? In what century?
1914.
So a bunch of sailors in 1914 claimed to have seen the sun in a place it shouldn't be.
No, the sun was fine. The thing is, the sun was rising, and they saw a silhouette of a mountain, right? So when they drew on their nautical chart where the sun was rising from, it intersected a mountain in Japan.
The sun intersected a mountain in Japan.
No, their line of sight to the sun intersects a mountain in Japan.
Okay. And based on
they're looking at the sunrise, they see the sunrise and they see the sun still, a mountain in front of it, right? The sun is silhouetting a mountain. They go, oh, damn, there's nothing out there. There's no land out there. Let's look on our nautical charts. Okay, let's draw a line on our chart to see where are we going to intersect land? So where it intersects land was Japan.
And so they then concluded that mountain must have been the one in Japan.
Well, if there's no other land, then that's the only thing it could possibly be. If you have floating mountains.
So it's the only thing that it could possibly be based upon
there's no other land in that water. Is this hard to comprehend? There's no other land in that water. There's the sea between Japan and North Korea and China is well traveled. There's no hidden islands there.
Sure. Okay.
And well traveled for about 4,000 years. Sure. But this isn't the only types of these observations. So in the Southern Ocean, the U.S. Geospatial Agency has a Southern Ocean sailing guide, and it says right in it, it is not uncommon to see mountains 300 miles away. Think about that for a second. A mountain 300 miles away should be 9.75 miles underneath the horizon. That's with refraction. Without refraction, it's like 11.25 miles. Mount Everest is 5.25 miles tall. So, it would have to be, that mountain would have to be 2 times the height of Everest for them to see it.
I mean,
this is in a U.S. Geospatial Agency publication. Now they print this stuff. They don't realize the consequences of what they're printing.
Sorry, why can't refraction affect this?
Oh no, he can extend the numbers. 11 miles and 9 point something, right?
Listen, so if you put in the so-called standard refraction, which is baseless bullshit, and I can tell you why it's baseless bullshit.
Well, I mean, standard refraction would. My understanding of weather is a little bit more limited than my knowledge on other topics, but can't the refractive index of air change wildly?
He's talking about the standard. You know what the standard is?
Well, yeah, but what about the real one? I mean,
the real one
was an average, and then you can have it vary from the average, right?
Yeah, in measurements, actual measurements, empirical measurements of what refraction is are nowhere close to.
Sure, I imagine it varies a lot more wildly. And the standard is probably just going to be like your average, you know. So how do we know what the index of refraction of the air was on that specific day that those 19th century
they
sailors
said it's not uncommon. It isn't just like that day. It's just not uncommon. It's kind of like a well-known thing that in the Arctic regions, in this particular region, the thing is, the Southern Ocean has a very low humidity. There's very little particulates in the air, so you can see incredibly far because you don't have haze or other shit in the air that you're looking through.
Okay. But again, like
what you're saying is
the refraction of air can vary.
A non-uniform medium with weather events.
Oh, I'm going to look up exactly what the angle is.
Consistent enough,
whatever the angle is,
to extend it to 300 miles constantly. It's going to be uniform. The non-uniform medium of the atmosphere is going to be uniform.
Uncommon,
no, can I finish, man? I'm getting a little tired of you interrupting people.
Oh.
So
sorry.
The atmosphere isn't uniform. But what you're saying is it's staying uniform enough that constantly you can see further than you should be able to on the globe because refraction is always the same amount. That's what you're saying.
I'm not saying... No, I'm not saying it's all... I'm saying that refraction can vary wildly, like, based on, like, the air pressure that day, the humidity of that day.
That would be a logical inference, and it would be an uncommon, not a common event.
So the downward tilt would be 4 degrees. So whatever they're looking at, right, would have to be picked up 4 degrees.
Okay.
Constantly.
And
wait,
what was this relation to the neutrino experiment?
8 solar diameters. That's 8 solar diameters, just so you know. The sun is supposed to be...
The neutrino experiment is actually kind of similar to this event that you're explaining, with the benefit of neutrinos don't experience refraction. So, like, that's not an issue for
underground.
See, we can eliminate, and I'm going to tell you, we can eliminate, so the globe Earth excuse is refraction is causing things to be lifted up. There is nothing to support that. Literally not a goddamn thing. And I'll tell you why. Because refraction is frequency dependent, the wavelengths of light. And never has anybody done a long-distance observation and saw chromatic aberration of mountains, shit like that. And that's what happens. That's what would happen. You have a splitting of the wavelengths of light. So by the time the light reaches your eye or camera or whatever, after 200, 300 miles, you're going to have this rainbow halo effect. This is why Isaac Newton went to reflector lenses. Or reflector telescopes, right? So the Newtonian reflector was the first reflector telescope, is because when you make a refracting lens, thicker, the frequencies of light separate, and you get something called chromatic aberration. We don't see this. No one's ever seen this. No one has ever looked out in a distance, right, from the top of a mountain and said, "Look, everything looks like it's surrounded in a rainbow."
Oh, I get you now. So like the air acts like a prism.
I didn't consider that.
I see.
Yeah.
No, there's actually
I didn't consider that.
So there is a paper. There's someone's master's thesis, right? There was a laser test. Now it was I don't know the name of the observatory. There's an observatory in Hawaii, right? So they're trying to figure out how to put adaptive optics on their telescope, right? So they have to account. They need a way to determine how much refraction there is in the air, right? So they did this test where they shine a laser beam from one island to the other, 130 kilometers. So they modeled this, and the only way to get the laser using the model, right, the refraction model with the standard lapse rate, temperature, all this stuff, you have to tip the laser beam up like 40 degrees in the model. But when you actually do it, they didn't have to do it when they actually did the experiment. And so we have this refractive model. So when they ray trace it out, the beams, they did 4 different frequencies of light, they're separated by something like 60 meters. So if you shine a blue laser and a red laser, they're going to have a separation of 60 meters by the time they get to the other side.
No, I get what you're saying.
What they actually did find out, what they did test, they tested a different model. They tested a turbulence model. that because we can all admit that things like, I don't know if you ever seen the skunk bay, right? So you can take a photo one day, things seem to move around, right? Shift around. But it's not because of refraction, it's because there's turbulence in the air. Air moving around causes light to deflect.
Okay.
It's not just refraction. It's the only thing that moves things around. So this is not like we can get to like Airy's failure, and that was a whole other thing, the Brazil effect.
So that's a very good point, and I'll have to do some more research on that on my own time and give that some serious thought.
Well, I just thought of this I don't know, a couple weeks ago. Hold on, this whole refraction thing has been being argued between flat Earth and globe Earth for 5 years. Okay, so what do we observe when light is actually refracted? We make lenses, right? We know, we design a lens. We have to compensate for all these other things. So what are the things they have to compensate for? Especially if the lens is thick, right? You got the air, light's going 270 miles through the air.
I get that.
You have to compensate for these things.
No, that is a very interesting
point. Because there's this thing where there's this thing the empirical data does not match the model. There's no doubt about that. If you go and look at all the papers on terrestrial refraction and look at them, they'll have their meteorological measurements, and then then they'll plug those into the model, and the model predicts greater deflection than what's actually measured in the field. And this is over and over and over again. I've seen papers where they actually compare 6 different models, and none of them match what they actually measure. I have one that says, I sent it to Sirius yesterday. So when they dig a tunnel through the Alps, right? So this is a thing in Switzerland. They're always digging tunnels because because it's all mountains, right? So they have to, when they dig a tunnel, they have to be very precise. They're digging through a freaking gigantic mountain. So, and they're digging from both directions. So if they're off a little bit, by the time they meet at the center, they're doomed, right? The tunnels are missing each other. They aren't meeting at the center. But they have to account for lateral refraction, right? Because tunnel walls heat up. So what they did was, they empirically tested, refraction by heating up bricks, right? And then shining light by the bricks and then measuring how much the light is deflected. And